Okay, I want to look more at graphing rational functions in the way of two rational parent functions. Really, if you deal enough with the rational functions, you'll find out that there are an infinite number of rational parent functions that look a whole lot of different ways. But we're going to focus mostly on rational functions that look one of two ways. The first parent I want to deal with is f of x equals 1 over x. And this is often called the reciprocal function. I'll write that down. And what you can do here, if you want to graph this, you can just think about, well, what happens when you plug in different values for x. So I'm going to start up here in the first quadrant. If I do 1 over 1, I get 1. If I do 1 over 2, I get 1/2. If I do 1 over 3, I get 1/3 and 1/4 and so on. So I'm going to start seeing the asymptotic behavior. It's going to get close to the asymptote, which is, for this one, the x-axis. If I look between 0 and 1, if I did 1 over 1/2, say, 1 over 1/2 is 2, 1 over 1/3 would be 3, and so on. I'm going to start getting a curve that looks like this. Getting really close to the asymptote. What if I move down, what if I look at negative x inputs? Well, if I do 1 over negative 1, I get negative 1. If I do 1 over negative 2, I get negative 1/2 and negative 1/3. And what this is really just going to be a reflection of the other curve. That's a rough sketch. Not perfect, but pretty good. Should make that a little bit more flat against the axis. So we see here again, we have asymptotes, and we know that the curves get really close to the asymptotes. What do I see? My domain and range. Well, 1 over x, clearly x cannot equal 0 because I can't divide by 0. So my domain is everything but 0. So I go from negative infinity up to, but not quite reaching 0, and then I skip and go from things that are just a little bit larger than 0 to infinity. And that's what this means. This means I'm skipping over 0. For my range, well, it's the same thing. If I think about the way I find asymptotes, 1 over x, the degree of the denominator is larger, so that should sound familiar. So I can tell that my horizontal asymptote is y equals 0. My vertical asymptote was x equals 0. So my range will be written the same way as my domain. Okay? Now, of course, I can transform this. I can shift it up, down, left, right. If I change this 1, if I make it a 2 or 3 or something, that will change how the graph looks. In particular, it will change how closely this hugs to the asymptotes. And of course, I can reflect it, and rather than two curves in these quadrants, I could have it more like up here and down here. But it will still look generally like this, and I can still predict the domain and range fairly easily as everything but the asymptotes. And I can write this in other forms. We talked about this transformational form in class, and it's in the previous video. If I do y equals a over x minus h plus k, and then I can incorporate all my transformations. A more general form, if you ever see something that is just the quotient of two linear binomials, that would also look something like this. Now, of course, I could make this more complicated if I included holes. We're going to discuss that minimally in this class, but that is a possibility. All right, let's take a look at the other parent function that we do want to know. And that's not the reciprocal function exactly. This is 1 over x squared. So 1 over x squared is going to look a little bit different. If you think about this, if I put in, say, 1 for x, well, I know that 1 squared is 1. So 1 over 1 squared will still be 1. If I do 2, if I make x 2, then 1 over 2 squared, that is 1 over 4, or 1/4. If I put in 3, I'll have 1/9. And what I will get is that this will approach the x-axis asymptote even faster than the previous parent did. What if I look at the negative numbers? Well, if I square negative 1, I get positive 1. So 1 over negative 1 squared will be 1 over 1. And just get that. And I apologize, I should maybe write some of this down. X, negative 2, negative 1, 0, 1, 2, 1 over x squared. So again, I cannot enter 0 in for x. If I do that, I will be dividing by 0, so that tells me my vertical asymptote is x equals 0. My domain will be everything but 0. But when I enter in these other things, if I enter in 1, I'll have 1 over 1 squared. If I enter in 2, I'll have 1 over 2 squared, which is 1/4. If I enter in negative 1 squared is 1, so this will be 1 over 1. Negative 2 squared is 4, so 1 over 4 is, again, 1/4. So what I'm going to see if I look at this graph is something which is symmetric about my vertical asymptote. Now, something to keep in mind when you're graphing these is, even if you check with a calculator, you'll find that most of the points on these curves are not particularly useful. They mostly come out to fractions or strange decimals. So you're not going to be able to get a particularly good graph. Usually a couple points on either side is sufficient to just get a general idea. Pay attention to asymptotes, certainly, and go from there. So my domain, going back over here, well, we said that x cannot be 0. For my horizontal asymptote, the degree of the denominator is greater, which means the horizontal asymptote is, again, y equals 0. So for my domain will be everything but 0, negative infinity up to 0, but not quite 0. My range, well, what I can see here, different than the last parent function, everything is above the asymptote here. So what I can say is my range is 0 to infinity. Okay, notice there's a single interval because all of the y values on this curve are greater than 0. Now, of course, I could transform this. How could I transform this? Well, if I put like a 2 or a 4 in the numerator, or a negative, or if I added something out here, if I made x squared something like x minus 5. So basically, if I put in transformations, this is that nice transformational form right here, y equals a over x minus h squared plus k. So if you ever see something like that, just be aware this is in the same family as this function, so you know it looks something like this. And again, this is not the only way it could be written. There are ways to just have it as a quadratic over another quadratic, but that's a little bit harder to spot. Alright, so keep this in mind. This is the general idea. These are what most of our rational functions are going to look like, which makes the ranges predictable. We mentioned before that the range can be kind of unpredictable for rationals because they can have turning points and minima and maxima if I start incorporating enough weird stuff. But we're going to focus primarily on things that look like this. So let's take a look at some functions and graphing them. So I want to graph each function, give its domain, range, and asymptotes. So I will make a note to myself. For my asymptotes, well, I have to consider that there should be a horizontal asymptote and a vertical asymptote. This is in that nice transformational form. I know that for large x's, this expression right here approaches 0. So the whole thing, f of x, will approach y equals -4, this number right out here. For my vertical asymptote, I know I have to look in that denominator and say that x should not be 2, so my vertical asymptote is x equals 2. If I want to graph this, what I want to do is just draw some asymptotes. One, 2, 3, 4. Good. I thought I miscounted there for a second. I draw in my asymptotes, and then I want to put in points to show this graph. How do I find those points? Well, of course, you could use a calculator. The other thing you could do is just plug in some numbers. Like I said, mostly the points in this graph are going to be pretty bad. So if you want to plug in x values, generally just go like 1 unit to the left and right of your vertical asymptote. If I put in, for example, 3 for x, well, if I put in 3, I would have -3 over 3 minus 2 minus 4. That is -3 minus 4. That's -7. 1, 2, 3, 4, 5, 6. There's -7 right there. And again, you could find some more points, but you know the general idea is now, going back to parent functions, since this is linear, this is not squared, I expect to see the two curves in opposite quadrants. So rather than having something down here, and up here, I'll be in these two quadrants. Okay, so you're going to go ahead and do that. You can check with a calculator. I'll get some more points right here. I know that's also on the curve. I get something that looks like this. Again, don't be afraid to just plug in some points. Don't be afraid to check with your calculator, but that's where you should come out to. On the other side, well, what would happen if I put in 1 for x? If I put in 1, I would have negative 3 over 1 minus 2 is negative 1. Negative 3 over negative 1 is 3. 3 minus 4 is negative 1. So I will see that. And again, you can check. If you put in 0, it's a little bit harder. You'll have 3 halves minus 4. 3 halves minus 4 is negative 2.5. And if I go ahead, 1, 2, 3, go right there. Those are some good points on this curve. And what I want to do is just as best I can put a nice curve through this. That's why this looks weird. I put that point in the wrong place. I'm sorry. Okay. So it looks something like that. And again, you can get more points just by plugging stuff in or check with the calculator, but that's the general idea. So my domain, well, my domain, I have no holes or anything here to worry about. My domain, x goes from negative infinity up until I reach this asymptote, and then on the other side of the asymptote, I have an infinite number of points. So I can see my domain is everything but 2. So in interval notation, we can say negative infinity to 2, union 2 to infinity. For my range, well, all of my y's down here, I am less than negative 4, and on this part of the curve, I am greater than negative 4. So my range will look similar. Negative 4 to infinity. And again, if I wanted to figure out things like y-intercept or x-intercept or increasing and decreasing, I can see that this is increasing over the entire domain. If I wanted to figure out y-intercept, I already did that when I was plotting points. You can substitute 0 for x. If I wanted to figure out an x-intercept, well, in order to do that, you'd have to solve the equation 0 equals negative 3 over x minus 2 minus 4, which is not too bad. What you should get is 2 3/4, so 11/4. No, that's wrong. I guess I now have to solve it to show you that we know how this works. 4 equals negative 3 over x minus 2. Oh, I know what I did. So 4 times x minus 2. 4x minus 8 equals negative 3. 4x equals 5. Your x-intercept would be x equals 5/4, or the x-intercept order pair 5/4, 0. All right. Anyway, I digress. That's how you graph this. Let's take a look at another example. So here, I want to figure out domain, range, asymptotes. So, horizontal asymptote, vertical asymptote. This is not in that nice transformational form. I see 2x over x. 2x over x is essentially 2. So I know my horizontal asymptote, y equals 2. My vertical asymptote, I look in the denominator and x equals negative 4. Should be my vertical asymptote. For my domain, I know I will have to exclude both of those things, but again, I'm going to graph this just to make sure. Y equals 2 is up here. X equals negative 4. 1, 2, 3, 4. And I expect, since these are both linear binomials, I expect that my curves will either be up here and down here, or in this quadrant and this quadrant formed by the asymptotes. So again, plug in some values. If I go 1 unit to the left and right of my vertical asymptote, that will usually be good. So for instance, if I put in negative 3, if you enter in negative 3 for x, you will have negative 6 plus 9 over negative 3 plus 4, which is 3 over 1. Okay? So 1, 2, 3, right there. If I enter in negative 5, I would have negative 10 plus 9 over negative 4 plus 5, negative 5 plus 4, excuse me, which is negative 1 over negative 1, which is 1. And again, you can get some more points. Like I said, they're mostly going to be pretty bad, the points. So I'm going to go ahead and just put a curve through these points. I can see based on these points that I should be down in this quadrant. And up here. And again, that's part of that first rational parent family, the reciprocal function. My domain will be negative infinity to negative 4, union with negative 4 to infinity. My range, from negative infinity, I go up, and I go up to positive infinity, but notice I'm skipping 2 in the middle. So negative infinity to 2, union with 2 to infinity. And again, if I wanted to find x-intercepts or anything like that, I could do it. If I wanted to find y-intercept, well, the y-intercept, if you put in 0, I'll go ahead and write this down. The y-intercept, if I substitute 0 for x, I will get 9/4. It's pretty simple. If I wanted to figure out the x-intercept, well, again, I'd have an equation to solve. To figure out the x-intercept, 0 is equal to 2x plus 9 over x plus 4. If you think about solving this, well, you'd multiply x plus 4 to the other side to get it out of the denominator, which would just leave you with 0 equals 2x plus 9. And this is something we should know. If a fraction equals 0, the only way that can be true is if the numerator equals 0. So my x-intercept is negative 9 halves 0. Negative 9 halves, negative 4 and 1/2. So that looks pretty accurate with what I graphed. Okay. So again, that's a look at what the curve looks like. That's domain, that's range, that's x-intercept and y-intercept. It also might have made sense to find these beforehand, so I could have had maybe a bit more accurate graph. But this still agrees pretty well with what I sketched. All right, let's take a look at another couple examples. Here, notice in both of these examples the denominator is squared. And I apologize, these are a little bit too similar for my liking. I should have made them a little bit more different. But let's go ahead and take a look. Domain, range, asymptotes are what I want to focus on. Domain, range, horizontal asymptote, vertical asymptote, so I can label my work. Well, I can see here that in that denominator, x cannot equal negative 3. There are no common factors to the numerator, so I can expect that that will be my vertical asymptote, x equals negative 3. For my horizontal asymptote, the degree in the numerator is greater, the degree in the denominator is greater, which means the horizontal asymptote must be y equals 0, the x-axis. So what I'm going to do is sketch my asymptotes. X equals negative 3 is right here. If the axis is your asymptote, if the x-axis is your asymptote, you don't really need to sketch that. I will do it just to make sure I don't cross it and do something silly. And now, if you want to figure out values, just substitute in some points for x. And you know that this is totally symmetric. What I see over here, I should see over here. So if I substitute negative 2 for x, 4 over negative 2 plus 3 squared. Well, that's 4 over, this is 1 squared, so this is just 4. 1, 2, 3, 4. And you can go ahead and keep substituting in values. If you put in negative 1, for example, you will have 4 over negative 1 plus 3 squared. That's 2 squared. This is 4 over 4, so that makes this 1. And you could keep going. If you put in 0, you'd have 4 ninths. 4 ninths, which is a little bit less than 1/2. But at that point, the points are going to start getting kind of nasty and just be fractions that don't graph particularly well. So get this and come down here. And I know I will see the same thing on the other side, because this is, since that is a square denominator, since there's a square in the denominator, this will be symmetric about the vertical asymptote. So just draw it getting close to those asymptotes, and I can figure out the domain and range. The domain is everything except negative 3. And the range is everything greater than 0. So 0 to infinity. Now, of course, I could figure out the y-intercept. I said it a minute ago, it was 0, 4/9. If I wanted to figure out the x-intercept, well, pretty clearly there is no x-intercept, because the x-axis is my asymptote. Now, mind you, a rational function can actually cross its horizontal asymptote somewhere in the middle of the graph. But I can see right here this definitely does not cross the asymptote. And for these parent functions, we can expect that it won't cross the asymptote. So for x-intercept, you can just say none. Okay, one more example. G of x equals -5 over x minus 3 squared plus 3. So if I figure out my asymptotes, x equals 3 will be my vertical asymptote. And this is in the nice transformational form. There's a 3 over here too, so y equals 3 will actually be my horizontal asymptote. And I can see the denominator is square, so I'm expecting something like this, although that -5 makes me think this is probably reflected downwards. So again, let's put in some values. My asymptote, my vertical asymptote, was x equals 3. My horizontal asymptote was y equals 3. And what I need to do here, I need to figure out, okay, well, what happens when, say, x is 4? Well, if I put in 4 for x, I have this. -5 over 4 minus 3 squared. This is 1 squared, which is 1. So this is -5 plus 3, which is -2. And I know it's symmetric, so I'll get the same thing over here. And you can try putting in a couple more points. If you put in 5 for x, well, if I put in 5 for x, it's a little bit harder to do, but I will have -5 over 5 minus 3 squared plus 3. That's -5 fourths plus 3. -5 fourths, that's -1 and 1/4. So 3 minus 1 and 1/4 is 1 and 3/4. Again, you see why the calculator can be useful for something like this. But I get a point right here. Like I said, most of these points are not going to be very good. So 1, 2 points, and then just a general idea of what the curve should look like is about all you want to do. About all you can do. That's why one of the big things we focus on, how to find the asymptotes. What's the domain? What's the range? How can I find x and y intercepts? Try and make it smooth. My pen is not helping me out right here. That looks a little rough. For my domain, well, I can see that x takes on all values except for 3. So there, that is an interval notation. For my range, well, I can see that y will take on all values which are less than that 3, the value from my horizontal asymptote. So my range will be -infinity to 3. If I wanted to figure out my x-intercepts, be careful here because I would have 2. I could solve those. It would require some square rooting. All right. I'm going to go ahead and do the one last example that is right here, and then stop. So you're asked here to find asymptotes, holes, x and y intercepts of this function. So what you need to do then is factor. And this was supposed to have an x right here, I can tell you that much. That's definitely a typo. Okay. So if I try and factor this, in the denominator I can take out a 5x and be left with x squared minus 4x minus 12. Up top, you can factor this by grouping. If you do factor that by grouping, I can tell you that you will have x squared minus 4 times 3x plus 7. And if I factor this all the way, I will have 3x plus 7 times x plus 2, x minus 2. X squared minus 4x minus 12, well, that is x minus 6 times x plus 2. And you're asked about asymptotes, holes, x and y intercepts for this function. All right. Well, first thing to note, x plus 2 is a common factor to the numerator and the denominator. So that means that's telling me about a whole. So for asymptotes, I'm going to make a note to myself, horizontal asymptote, vertical asymptote, and I can also say I have a whole, x-intercept, y-intercept, I have all that stuff. So for my vertical asymptote, well, first off, I have a whole at x equals -2. For my vertical asymptote, well, these distinct factors to the denominator will each give me a vertical asymptote. This would be a function that has two vertical asymptotes, x equals 0, x equals 6. If I wanted to figure out my horizontal asymptote, well, I look back here and I know I compare the leading terms. 3x cubed over 5x cubed is essentially 3/5. So my horizontal asymptote is y equals 3/5. X-intercepts and y-intercepts, how do I do those? Well, x-intercepts, remember you're solving the equation 0 is equal to this. X plus 7. And I'm going to rewrite this slightly. Now we talked about this a minute ago. The only way a fraction can equal 0 is if its numerator is 0. But be careful here. This whole does actually make it so you might want to say that there's an x-intercept at -2, 0, but we know there's actually a whole at -2. So what I'm going to do here, the only way this can work is if 0 is equal to 3x plus 7 or 0 is equal to x minus 2, which will give me two x-intercepts, 2, 0, and from this I will have -7/3, 0. If I want my y-intercept, that means I put in 0 for x. I could get it from the factored form, but it's actually easier to get it from right up here. Except, if you put in 0 for x, what happens? Well, up top, I'll have 0 plus 0 minus 28. In the denominator, I will have 0 minus 0 minus 0. -28 over 0, that's not defined, which means my y-intercept doesn't exist, which we already knew because of that vertical asymptote. So I'm just going to scratch this out and write none. Hopefully this is helpful. Of course, I wish I had more time to spend on this in class. Ask some questions.